The forest wakes in layers. First, the faint rustle of insects navigating the canopy's underbelly. Then the rhythmic wing beats of bats retreating into daylight refuges. Soon after, the first piercing calls of birds break across the morning air. But these are only preludes, background murmurs compared to what follows. As the sun's rim glows against the Amazon horizon, the jungle trembles with a sound so massive, so resonant, that it feels less like a call and more like a force of nature itself. The howler monkey has begun its morning proclamation. To hear a howler monkey is to feel it. The roar does not merely pass through the ears, it vibrates against the chest, rattles branches, and echoes through valleys as if the very forest itself were groaning awake. This is no ordinary call. It is the deepest, most powerful voice among all land mammals. A single troop can project its chorus nearly 3 miles, a range that astonishes even seasoned biologists. To understand how such a sound is possible, one must look not at the mouth, but at the throat, at a structure called the hyoid bone. In humans, it is small and unremarkable, anchoring the tongue. In howlers, it is a hollow, balloon-like chamber, a natural amplifier evolved for one purpose: to make the forest listen. This adaptation is not a novelty, but a survival strategy refined over millions of years. Howler monkeys live in relatively small groups compared to other primates. Unlike baboons, which rely on sheer numbers, or capuchins, which use agility and teamwork, howlers defend vast territories through sound alone. Their amplified roars are a form of acoustic fencing. When one troop bellows across the canopy, rival groups miles away respond, and a kind of sonic map is drawn through the trees. This prevents costly physical confrontations. Blood need not be spilled when borders are carved in sound. Evolution has written efficiency into their anatomy. A fight avoided is energy saved, and in the Amazon, energy is survival. The roars also serve as a morning ritual, synchronizing the movements of the troop. Each member, from the dominant male to the youngest juvenile, rises with this signal. As branches shake with their ascent, the chorus continues, strengthening social cohesion and ensuring that stragglers remain close. In the dense, visually obstructed rainforest, sound is often a more reliable tether than sight. For predators such as jaguars or harpy eagles, which rely on stealth and ambush, the knowledge that an entire troop is awake and alert creates a deterrent. Few hunters are willing to attack a group whose presence is broadcast so loudly across the jungle. But the roar does more than protect. It defines ecological rhythms. When the howlers call, other species listen. Certain birds delay their own dawn songs until the forest quiets, preventing their delicate notes from being drowned. Insects shift their own acoustic signals, adjusting to avoid overlap. Even other primates, such as capuchins, alter their foraging patterns based on the known presence of a howler troop. In this way, the roar is not simply communication within a species, it is a cross-species cue, a pulse in the jungle's daily schedule. To live so loudly comes with physiological costs. Producing such sustained guttural calls requires immense breath control and muscular endurance. Studies have shown that male howlers with the largest hyoid chambers often have smaller testes, a biological trade-off between vocal dominance and reproductive capacity. It is as though nature has forced a choice: invest in the ability to command territory through voice, or in the ability to spread one's genes through frequent mating. This balance shapes troop hierarchies. A male with a thunderous roar may control prime feeding grounds, but his reproductive monopoly can be challenged by younger rivals with smaller voices, but greater fertility. Evolution's compromises echo even in the forest's loudest call. The diet of howler monkeys further explains their reliance on such strategies. Unlike their agile fruit-hunting cousins, howlers subsist largely on leaves. Leaves are abundant but poor in calories, forcing a slow lifestyle. Their days are marked by long hours of rest, conserving energy in the heat of the canopy. This low-energy economy means they cannot afford prolonged battles or high-speed chases. Instead, they have evolved to dominate through presence, through the kind of voice that ensures space, deters rivals, and minimizes the need for exertion. The roar, then, is an extension of their ecology, a sound as deliberate and energy-efficient as the animals themselves. What emerges from this understanding is a curious paradox. These monkeys, known for their ferocity of voice, are among the most lethargic of primates. They spend up to 80% of their day resting, draped languidly across branches, barely moving except to shift from one leafy cluster to another. The forest may shake with their calls at dawn, but by noon they are motionless silhouettes against the canopy, blending into the stillness of leaves. Only in the balance of sound and silence can the species survive. Yet perhaps the most intriguing aspect of the howler's roar is not what it achieves within the forest, but what it suggests beyond it. Scientists studying bioacoustics have noted that low-frequency calls, like those of the howler, can resonate with unusual persistence, bouncing through layers of vegetation and carrying far beyond their apparent range. Some frequencies even interact with the ground, transmitting vibrations detectable by other animals at the forest floor. In effect, the howler is not only broadcasting through air, but potentially shaping a wider acoustic environment that includes soil, water, and even distant echoes. This is where the concept of the sound code begins to take shape. If the howler's roar establishes a kind of baseline, a dominant frequency against which other signals can be layered, then it may be more than mere territorial declaration. It could be the opening note of a jungle-wide broadcast. When electric eels release their coded pulses underwater, or when caimans rumble with infrasonic growls, these signals might align with the existing resonance set by the howler. The jungle, in this view, is less a collection of isolated voices and more a polyphonic system, each species tuning into and layering upon the others. The implications stretch further still. The Amazon is one of the noisiest habitats on Earth, yet it is also one of the most acoustically organized. Researchers using soundscape ecology have found that different species occupy specific acoustic niches, avoiding direct competition by shifting pitch, rhythm, or timing. The howler monkey, by virtue of its unmatched volume and frequency, may act as the foundation of this entire system, the carrier signal that allows other transmissions to be modulated and heard. If so, its roar is not just a warning, not just a morning song, but a vital pillar of the rainforest's hidden architecture of sound. Consider the perspective of a listener beyond the forest. Were one to capture these overlapping signals, the roars, the rumbles, the pulses, the clicks, and translate them into patterns, would they resemble random noise or something more structured? The idea that evolution could inadvertently produce a coded system of broadcast is not far-fetched. After all, each adaptation serves a purpose within its own niche, yet when combined, they may create an emergent pattern larger than the sum of its parts. The howler monkey, then, becomes not merely the loudest voice of the jungle, but the conductor of a vast orchestra whose symphony we have only begun to hear. For now, the roar remains both a marvel of biology and a riddle of ecology. As the morning fades, the howlers retreat into silence, their great effort spent, their territory secured. The forest resumes its chorus of birds, insects, and rustling leaves. Yet the echoes of that thunderous call linger in the canopy, resonating like the aftershock of a storm. And in that lingering sound lies a question. What if this is not just communication, but calibration? What if the howler's voice is the opening key of a code that unites the Amazon into one vast living broadcast? The Amazon at night is a world half hidden, half revealed. Above the surface, the forest hums with insects and the occasional splash of a caiman breaking the silence. But beneath the waterline, in the slow-moving backwaters and murky channels, the darkness deepens into something impenetrable. Vision becomes almost useless here. The water is too clouded by sediment, too thick with organic matter. In this shadowed realm, survival belongs not to the sharp-eyed, but to the sharp-sensed. And no creature embodies this truth more powerfully than the electric eel. Despite its name, the electric eel is not truly an eel, but a knife fish, a long-bodied relative that has transformed the Amazon's murky waters into its own electric theater. To watch it is to see almost nothing, for its movements are subtle, its body blending with drifting debris. But to sense it, if one were a fish in its presence, is to enter a storm of invisible fields. At will, the eel generates electricity, not just in spectacular high-voltage bursts that can stun prey or deter predators, but in low, deliberate pulses that function like a coded language. The power behind this ability lies in specialized cells known as electrocytes, aligned in thousands within the eel's body. Each cell is like a miniature battery, and when triggered simultaneously, they release their charge in unison. In its most extreme display, the electric eel can deliver shocks of up to 600 volts, enough to jolt a horse and certainly enough to paralyze an unsuspecting fish. But it is the subtler discharge that truly reveals the eel's evolutionary genius. With rapid, low-voltage pulses, the eel speaks to its environment, creating an electrical landscape through which it navigates, hunts, and interacts with others of its kind. This system is not crude or simplistic. It is nuanced, layered, and surprisingly flexible. A steady series of weak pulses maps the riverbed, detecting objects and living creatures as surely as echolocation guides a bat. But when two eels approach one another, the pattern shifts. Suddenly, the bursts shorten, quicken, or take on rhythms that resemble phrases. To the untrained ear, or in this case the untrained sensor, the effect is mere static. To another eel, it is identity, intent, perhaps even emotion encoded in voltage. One pulse pattern might signal aggression, another courtship, another reassurance. What seems to us like noise becomes to them a lexicon, a private Morse code written in electricity. In these hidden dialogues, the river transforms from silence to conversation. Scientists observing wild eels have documented exchanges that resemble questions and answers, one individual producing a burst, another responding with its own sequence, as if in debate. During breeding seasons, males employ elaborate electrical displays to court females, layering their signals with specific frequencies that differentiate them from rivals. A female receptive to these patterns chooses a mate not by appearance, since the water affords little visibility, but by the quality of his electrical song. Predation adds another dimension to this code. The eel's hunting strategy is unlike anything else in the animal kingdom. When searching for prey, the eel issues a series of doublets, pairs of rapid pulses, that flush hidden fish from vegetation. The sudden increase in electrical activity startles the prey into movement, betraying its position. Once the target is revealed, the eel unleashes a torrent of high-voltage discharges, overwhelming the nervous system and rendering escape impossible. In effect, the eel has evolved a two-step weapon. First, a coded signal that manipulates behavior, then a lethal shock that ensures capture. It is both hunter and puppeteer, bending other animals' actions to its advantage. But there is danger in broadcasting. The electrical emissions that guide the eel's world can also be intercepted. Predators attuned to electric fields, such as certain catfish, may detect the eel's signals. Rivals, too, can eavesdrop, intruding on a territory or challenging for mates. To mitigate this, some electric fish, including the eel's relatives, shift the frequency of their signals, adopting dialects that reduce interference. It is a form of cryptography, an evolutionary encryption to protect the message from unwanted receivers. Whether electric eels themselves practice such sophisticated frequency hopping remains a subject of research, but the principle is clear. In a world alive with electricity, communication must adapt as much as combat. The environment itself shapes this strategy. In turbid waters where sight fails and sound is muffled, electricity provides a channel of extraordinary reliability. Unlike light, which scatters in suspended sediment, or sound, which loses clarity amid competing calls, electric fields penetrate consistently. They allow the eel to build a sensory map of its surroundings, one that functions even in total darkness. In this way, the eel becomes a navigator of the unseen, crafting a private universe of perception. This is where the sound code expands into new territory. While the howler monkey claimed the canopy through air, establishing a baseline roar that echoed for miles, the electric eel colonizes the river with voltage. Its signals are not airborne, but aquatic, not heard by ears but felt by nerves. Yet both fulfill the same role. They impose order on a chaotic environment by laying down a dominant frequency. One in sound, the other in current. Together, they suggest a multi-medium network that spans the Amazon's greatest barriers, land and water. There is another dimension worth considering, the relationship between electric eels and humans. Local communities have long respected and feared these creatures. Tales persist of fishers or livestock shocked to death by a single misplaced step in shallow water. Even scientific study carried risks. Early explorers described the eel as an aquatic thunderbolt, unpredictable and dangerous. Yet it is precisely this fearsome ability that draws our fascination, because in the eel's body lies a natural power plant. Its electrocytes are living batteries, its discharge is nature's demonstration of bioelectricity. The principles of this system inspired some of the earliest studies into electricity itself, influencing technology far beyond the jungle. What began as survival in muddy waters became the foundation for human innovation in physics and engineering. But within the eel's biology lies an even subtler lesson about life's adaptability. Consider the energetic cost. Maintaining electrocytes requires immense metabolic input. To fuel them, the eel must consume large quantities of prey, despite living in waters that are often nutrient poor. This challenge has shaped its physiology. Electric eels surface frequently to gulp air, supplementing the low oxygen of their environment with direct respiration. They are not fully aquatic in the conventional sense, but semi-air breathing, using their vascularized mouth to extract oxygen much like a lung. In this adaptation, the eel demonstrates a theme common to the Amazon's creatures. Survival is not about fitting into one niche, but bridging many. It breathes both water and air, hunts with both stealth and electricity, speaks with both silence and shock. For the sound code, this bridging role is critical. The eel's pulses resonate not only within the water, but also ripple outward, disturbing the surface, transmitting faint vibrations into the air. Birds and mammals may not perceive the signal directly, but the jungle itself records the disturbance, ripples against leaves, subtle shifts in the chorus of insects, the splash of fleeing prey. Just as the howler monkey's roar can influence creatures far beyond its own species, so too can the eel's electric Morse alter the rhythm of the river ecosystem. Predators move differently when eels are active. Fish alter their schooling behavior. Even amphibians, caught between land and water, sense the charge in their skin. In this sense, the eel is not an isolated phenomenon, but a node in a network of interactions. Its pulses carry meaning not just for other eels, but for the community of life around it. And when considered alongside the canopy's roaring primates, the swamp's rumbling caimans, the drumming ants, and the tapping tarantulas, it becomes increasingly difficult to dismiss the possibility that the Amazon is less a collection of voices than a coordinated broadcast. As dawn breaks above the river, the eel retreats into the shadow of a submerged log. Its night of hunting is done, its energy stores replenished. The water resumes its quiet flow, disturbed only by the occasional ripple of a fish. Yet if one could tune into the invisible, the river would still be alive with faint pulses, codes exchanged between unseen bodies in the current. To us, it is silence. To them, it is language. And perhaps, when layered upon the howler's thunder and the caiman's bass, it is part of something larger still, the hidden transmission of the Amazon, broadcasting through earth, air, and water, waiting for someone to listen. The Amazon at night becomes a theater of contrasts. Above the water, the forest hums with high-pitched insect choirs. Bats streak through the canopy with ultrasonic cries, and the occasional screech of a nightbird cuts through the dark. But in the swamps, something deeper stirs. Vibrations too low to be called sound in any conventional sense, a resonance that travels not through air alone, but through the very ground itself. The surface of a backwater lagoon ripples, though no wind disturbs it. The origin is a reptile, whose lineage stretches back to the age of dinosaurs. The caiman, summoning its world with a hidden growl. To witness this display is to encounter the strange power of infrasound, frequencies below the threshold of human hearing. Unlike the piercing roars of howler monkeys or the electric staccato of eels, the caiman's communication is felt before it is heard. A male positioning himself along the shallows inflates his body, forcing air through specialized structures in his throat. The result is a guttural vibration that rattles through water and soil alike, setting off concentric ripples across the swamp's surface. At times, the entire animal shudders as though the sound were shaking its very skeleton. For the caiman, this infrasonic call is both a declaration and an invitation. It is a territorial warning to rivals, announcing not just presence, but dominance. At the same time, it is a beacon to potential mates, a signal of vitality that travels across long distances. Because infrasound propagates more efficiently than higher-pitched sound, it can carry through dense vegetation, across riverbanks, even beneath the water, where it resonates in ways imperceptible to human ears. In effect, the swamp becomes a resonant chamber, amplifying the reptile's voice far beyond the limits of sight. The biology behind this feat reflects millions of years of crocodilian evolution. The caiman's larynx, enlarged and reinforced by cartilaginous structures, functions as a natural subwoofer. Air sacs within the throat expand, producing pressure that translates into low-frequency vibrations. When coupled with the animal's broad body cavity and contact with water, these rumbles reach intensities that can make the surface boil. Observers often describe it as a combination of thunder and tremor, a sound so physical that it seems to belong as much to the earth as to the animal. Yet the purpose of this communication extends beyond mating or territorial contests. In groups, multiple males may vocalize in succession, creating an overlapping chorus of infrasonic beats. The effect is similar to a drumline, synchronized pulses that travel outward, saturating the environment. Some biologists suggest that these choruses may help regulate spacing between individuals, preventing overcrowding in sensitive habitats. Others suspect a more social function, with the vibrations coordinating movements of females and juveniles across the swamp. The growl, then, is not simply noise but structure, a low-frequency architecture that organizes reptilian society. Predator-prey dynamics also intersect with this hidden language. Fish, sensitive to vibration, scatter when a caiman calls, mistaking the tremors for the approach of a massive predator. Birds nesting nearby sometimes flush into the air, unnerved by the resonance underfoot. For caimans themselves, this reaction can be advantageous. The sudden panic of prey species creates opportunities for ambush, with disoriented fish or frogs moving into striking range. Thus, the growl serves a dual function: communication to allies and intimidation to others. In an environment where stealth and sudden violence define survival, such multitasking is evolution's currency. What is striking about infrasonic communication is its invisibility to human perception. We often equate the jungle with loudness: the roar of monkeys, the shriek of parrots, the constant hum of insects. Yet the most powerful messages may be occurring below our auditory threshold. Elephants in Africa use similar infrasound to coordinate herds across miles. Blue whales broadcast through the ocean's depths with sub-bass moans that can cross entire basins. The caiman joins this global fraternity of low-frequency communicators, employing vibrations that weave life together beyond our capacity to detect. The swamp itself enhances this phenomenon. Water conducts sound 4 times faster than air, allowing vibrations to propagate with remarkable efficiency. Soft sediments beneath the lagoon further act as conduits, transmitting the growl through the ground like an underground cable. In this way, the caiman does not simply call across space, it occupies it, embedding its signal into the environment. For an intruding rival, the very earth may seem to declare the presence of a dominant male before the animal is even seen. From an evolutionary perspective, this strategy reflects the caiman's balance between energy and risk. Confrontations between males can be violent, with jaws capable of crushing bones and tails strong enough to break ribs. By using infrasound, rivals can establish hierarchy without necessarily escalating into combat. A larger, healthier male with a deeper, more resonant growl may deter competitors before a fight begins, saving both parties from costly injury. As with the howler monkey's roar, sound becomes a weapon of efficiency, one that shapes behavior long before physical contact. The resonance of the caiman also ties directly into physiology. Producing infrasound requires not just anatomical adaptations, but also muscular control and energetic reserves. Only males in peak condition can sustain repeated displays, making the growl an honest signal of fitness. Females, attuned to these subtleties, may choose mates not by visible traits, but by the depth and consistency of their calls. In a murky swamp where vision is limited, sound becomes the truest measure of health. But what role might these hidden frequencies play in the sound code of the Amazon? Unlike the howler monkey's piercing roar or the electric eel's staccato bursts, the caiman contributes a foundation. Infrasound travels farther than most signals, crossing barriers that would confound higher pitches. It resonates through multiple media, air, water, and ground, effectively binding disparate environments into a common frame. In musical terms, the caiman provides the bass line, the low, unshakable rhythm upon which other species layer their calls. Without it, the system lacks depth. With it, the broadcast becomes anchored, strengthened, and potentially extended to scales far beyond our imagination. Consider the possibility of overlap. A howler monkey roars in the canopy, its frequencies dominating the air. At the same time, a caiman rumbles in the swamp below, transmitting infrasound through earth and water. Though the two species are unaware of each other's intent, their signals intersect, creating harmonics that ripple through the ecosystem. Add to this the pulses of electric eels, the drumming of ants, and the tapping of tarantulas, and the jungle begins to resemble less a cacophony than a polyphony, multiple voices combining into one complex transmission. The caiman, with its subterranean voice, provides the resonance that unifies them. For humans, the challenge is recognition. Our ears are ill-equipped to detect infrasound, perceiving only the consequences: rippling water, vibrating earth, unsettled animals. Yet technology has revealed the patterns, recording frequencies that extend below 20 Hz, revealing rhythms hidden in the swamp's silence. Some researchers have speculated that such vibrations may influence human perception itself, producing sensations of unease or awe when experienced directly. The folklore of rivers haunted by spirits may, in part, be a cultural interpretation of caiman infrasound, a natural phenomenon transformed into myth by human limits. In the broader context of ecology, the caiman's growl highlights a principle that recurs throughout the Amazon. Communication does not exist in isolation. Every call, every pulse, every vibration has ripple effects, influencing not just the intended receiver, but the entire community. In the swamp, fish scatter, birds lift off, frogs adjust their calls, and rival males reconsider their positions. A single growl becomes a cascade of responses, binding species together in a web of cause and effect. This interconnectedness is the essence of the sound code, not a deliberate collaboration, but an emergent system born of necessity, survival, and evolution's unrelenting experiments. As night deepens, the swamp grows still. Moonlight reflects off the black water, broken only by the eyeshine of reptiles drifting just beneath the surface. Somewhere in the darkness, a male caiman exhales, then begins again, a low, resonant growl that makes the water shiver. It is a sound few humans will ever truly hear, yet one that resonates across the ecosystem with undeniable force. And as it echoes through water and earth, it lays down the baseline of the Amazon's hidden broadcast, a frequency that may stretch farther, last longer, and carry more meaning than we have yet dared to decode. The Amazon is often described as a place of giants, towering trees, vast rivers, predators with bone-crushing jaws. Yet some of the most extraordinary feats of organization and power belong to creatures that weigh less than a paperclip. Beneath the forest canopy, along sunlit paths cut through the undergrowth, an army is always at work. A ribbon of movement stretches across the forest floor, each unit carrying a green shard far larger than itself. From above, it looks like a procession of animated leaves, a living conveyor belt that never ceases. These are leafcutter ants, among the most sophisticated engineers in the natural world, and though their labor is silent to the human ear, the colony itself hums with a hidden language of clicks and vibrations. To step closer is to notice their dual nature. On one hand, they are individuals, tiny bodies with jaws sharp enough to shear through foliage, climbing stems and vanishing into tunnels. On the other, they are a collective, millions of bodies synchronized into a machine whose scale dwarfs imagination. And like any machine, communication is the key to coordination. For ants, deprived of voices in the mammalian sense, sound emerges from ingenious alternatives. Leafcutters stridulate, scraping one body part against another to produce faint clicks, sometimes drumming their mandibles against the very leaves they cut. Others drum against tunnel walls, sending tremors through soil that travel faster and farther than airborne sound. To us, these are whispers lost in the jungle's cacophony. But within the colony, they are orders, warnings, and instructions as vital as any military command. The ecological success of leafcutters hinges on this vibrational language. Consider the problem they face. A colony can exceed 5 million individuals, with countless foragers moving across dangerous terrain to harvest leaves. Without coordination, chaos would ensue. Ants would collide, trails would clog, predators would exploit the disarray. Instead, the clicks and drumming act like traffic signals. A worker, slowed by heavy cargo, emits vibrations that encourage others to assist in cutting or clearing the way. Scouts encountering danger broadcast alarms through rapid stridulations, causing nearby ants to scatter or to mount a collective defense. Even underground, vibrations carry critical messages through packed soil, allowing the unseen millions to act as though they share one nervous system. Leafcutters do not eat the leaves they harvest. Instead, they use them as substrate to cultivate fungus, their true food source. This agricultural system, one of the oldest examples of farming on Earth, depends on precision. The fungus is sensitive to contamination, temperature, and humidity. Ants maintain climate control within their chambers by excavating vents, adjusting tunnels, and redistributing leaves. Clicks and drumming help synchronize these tasks. When a chamber grows too warm, workers vibrate to signal excavation. When fungus shows signs of mold, alarm vibrations recruit specialized cleaners. In essence, the colony functions as a living greenhouse with communication networks as sophisticated as any human farm. Predator-prey interactions reveal further depths of this system. Army ants may raid leafcutter trails, forcing workers to abandon loads and retreat. Birds and anteaters also target the ants themselves, but leafcutters are not defenseless. Their soldiers, with disproportionately large heads and mandibles, defend trails with snapping jaws that can slice human skin. These defenders are summoned by vibrations, their deployment resembling a military reinforcement called to the front line. In this way, the ant's acoustic world is inseparable from its survival. Without clicks and tremors, the colony could not muster defense quickly enough to resist attack. The scale of leafcutter activity also impacts the forest itself. Colonies harvest up to 20% of local vegetation annually, shaping the growth patterns of trees and understory plants. Trails carved through the forest become permanent highways, altering the microhabitat. The soil they excavate enriches the ground with nutrients, aerates it, and changes its structure. Biologists often describe them as ecosystem engineers, a title they share with beavers and termites. Yet unlike beavers who dam rivers or termites who build towering mounds, the leafcutter's engineering is less visible unless one listens. The colony's faint clicks are the percussion of construction, a rhythm that organizes millions into an ecological force. From a sensory perspective, the ants' reliance on vibration makes sense. In the dim undergrowth and subterranean tunnels, vision is nearly useless. Chemical signals, such as pheromone trails, provide directional guidance but are too slow to transmit urgent information. Vibrations bridge the gap, fast, immediate, and localized. They provide the colony with real-time updates on traffic jams, intrusions, and workload. For ants, sound is not entertainment, not expression. It is infrastructure. What humans perceive as silence in the forest is often the product of our limitations. Place a vibration sensor near a leafcutter trail and the illusion dissolves. Suddenly, a background hum appears. The combined stridulations of millions, like the static of a distant radio station. The colony is not quiet at all, but alive with constant coded rhythm. To interpret it is to eavesdrop on a society as complex as our own, yet governed by instincts honed through natural selection rather than conscious planning. In the context of the sound code, this vibrational chatter becomes essential. If the howler monkey provides the baseline roar and the caiman the deep infrasonic rumble, the leafcutter supplies the percussive layer. Millions of clicks create a form of background static, not random but patterned, like the rhythmic beating of drums beneath a symphony. Their signals permeate soil, resonating through the ground in ways that overlap with the caiman's infrasound. Together, they bind canopy and swamp to the very earth beneath them, ensuring that the broadcast is not confined to air or water, but transmitted through the solid foundation of the forest itself. This perspective reframes the ants' work as more than ecological service. The endless cutting, carrying, and cultivating are acts of survival, yes, but also contributions to a larger acoustic fabric. While monkeys shout across valleys and eels pulse beneath rivers, ants lay down the rhythm of continuity, steady, persistent, unstoppable. Their clicks form the jungle's static, the background noise upon which all other voices are built. Without them, the broadcast might falter, lacking the percussive structure that organizes sound into rhythm. The irony is that the very creatures responsible for this hidden music are often dismissed as pests. Farmers see them as destroyers of crops, nuisances whose endless hunger reduces yields. And indeed, leafcutters can defoliate entire fields overnight, their efficiency rivaling machines. Yet in the grander scheme of the forest, their role is irreplaceable. By pruning plants, recycling organic matter, and cultivating fungus, they maintain balance in an ecosystem that thrives on cycles of growth and decay. Their clicking signals are not only communication within the colony, but the pulse of ecological renewal. From a human perspective, there is something humbling in this. Our species prides itself on language, on technology, on the ability to organize millions into functioning societies. Yet here in the rainforest, insects no longer than a fingernail have accomplished something strikingly similar, and they have done so for millions of years longer than we have existed. Their infrastructure is vibration, their machines are their bodies, their industry is ceaseless, and all of it unfolds in near silence to us, hidden only by the limits of our perception. As night falls, the procession continues. Ants march along their trails beneath the glow of the moon, carrying fragments of leaves back to subterranean chambers. Their bodies vibrate with stridulations too faint for human ears, but in the soil and within the colony, These signals spread like ripples. Clicks overlap with clicks, millions of tiny rhythms combining into a chorus of static. To the forest, it is another layer of sound. To the ants, it is life itself. And within the broader code of the Amazon, it is percussion, the constant drumming that ensures the jungle's hidden broadcast never loses its rhythm. The forest at night feels different than by day. Gone is the chatter of monkeys and the bright flashes of macaws. Instead, the air thickens with humidity, and the undergrowth comes alive with creatures designed for shadow. Leaf litter rustles, small eyes glow in reflected moonlight, and unseen wings beat against the heavy night air. Amid this hushed intensity, a tarantula emerges slowly from its burrow. Its body, a mass of hair-covered armor, seems built for quiet ambush rather than show. Yet as it steps forward, one leg lifts and falls with deliberate precision. Then another. To human ears there is nothing, only the faint crunch of soil. But to the right listener, to another spider hidden nearby, this is a conversation. The tarantula is speaking in vibrations, its voice written not in air, but in the earth itself. Spiders are often imagined as solitary hunters, relying only on stealth and venom, but in truth they communicate more than we realize. Tarantulas, like many of their relatives, use seismic signals, drumming their legs against the ground, vibrating their bodies, or tapping rhythms that travel as tremors through soil and leaf litter. This is not random noise. Each signal carries meaning, crafted by natural selection to be as distinct and functional as a bird's song or a primate's call. The problem for us is perception. Our ears are tuned to airborne sound in the human range of frequencies. Spiders operate below and beyond that range. In micro-vibrations, our species was never meant to detect unaided. Where we hear silence, they hear sentences. Courtship is where this hidden language is most elaborate. A male tarantula, fragile compared to the robust female he approaches, risks death with every mating attempt. His survival depends on sending the right message, and on her ability to interpret it correctly. With his legs, he taps a coded rhythm into the soil, announcing his identity and intent. If she accepts, her body vibrates in reply, signaling receptivity. If not, he may be attacked and consumed before he can retreat. Courtship drumming is thus both a love song and a test, a way of ensuring that only the most precise communicators pass on their genes. The stakes are life or death, and evolution has refined the system into something both subtle and exact. Territorial encounters are shaped by the same principle. A tarantula defending its burrow can drum a warning into the ground, discouraging rivals without resorting to a costly physical fight. Predators too may trigger these responses. The footsteps of a mammal or the scuttle of another arthropod create vibrations the tarantula interprets as potential threat. In such cases, the spider may either retreat or issue rapid, forceful taps designed to startle. Here again, seismic sound conserves energy, resolving conflicts through signal rather than injury. The precision of this communication depends on an extraordinary sensory system. Along the tarantula's legs are slit sensilla, tiny hairline cracks that deform in response to vibration. Each functions like a pressure gauge, detecting the slightest tremor from the ground. Combined, they create a seismic sense as sensitive as a finely tuned instrument. Some tarantulas can detect vibrations down to mere nanometers of displacement, meaning that the fall of a single raindrop or the passage of a beetle nearby is perceptible. Their world is one of constant tactile information, a conversation carried by the substrate rather than the air. What is remarkable is how this sense shapes behavior beyond communication. A tarantula sitting at the entrance of its burrow can track prey without ever seeing it, distinguishing the vibrations of a passing cricket from those of a larger predator. By filtering signal from noise, it responds only when the message indicates opportunity or threat. This is efficiency at its evolutionary finest. Unlike predators that rely on vision or hearing, both limited by darkness and distance, tarantulas thrive in environments where seismic cues dominate. They are tuned to the hidden rhythms of the earth. From a broader ecological perspective, this places tarantulas in a unique role. Their seismic signals overlap with those of ants, termites, and even larger animals whose movements resonate through the ground. In the dense acoustic jungle, where air is filled with roars, rumbles, and pulses, the substrate carries its own layer of information. Tarantulas are both participants and interpreters in this layer, fine-tuning messages that operate at the scale of centimeters but may ripple outward to join the larger soundscape. Predator-prey interactions reveal the tension in this hidden channel. A tarantula may rely on its seismic sensitivity to detect prey, but some of its predators have evolved to exploit the same medium. Certain wasps, such as the tarantula hawk, locate their hosts by sensing the vibrations of movement near burrows. In this way, the very signals that allow survival also invite danger. Evolution solutions are rarely free of cost. The tarantula's reliance on vibration is simultaneously its strength and its vulnerability. For humans, seismic communication can seem alien, almost mechanical. Yet it is strikingly common in the natural world. Frogs produce tremors during mating choruses. Small mammals thump the ground as alarm signals. Even elephants drum the earth with low-frequency rumbles that travel beneath our notice. Tarantulas, operating on a smaller scale, are part of this same evolutionary strategy, using the physical medium of Earth as a communication channel. By doing so, they bypass the crowded airwaves of the rainforest and carve a private channel through silence. Within the sound code, this role becomes critical. If howler monkeys provide the loud bass line in the canopy and caimans the infrasonic resonance of the swamp, then tarantulas contribute the fine details, the micro-signals that give definition to the broadcast. Their taps are the equivalent of punctuation in language, subtle markers that sharpen meaning. Imagine a symphony, without percussionists adding delicate cymbal taps or snare rolls. The music lacks texture. Tarantulas are that texture in the Amazon's broadcast, ensuring that the larger, louder voices do not blur into formless noise. There is an irony here. Humans often fear tarantulas for their size and appearance, imagining them as silent hunters. In reality, they are among the rainforest's quiet communicators, their survival tied less to venom than to vibration. They are engineers of subtlety, whose taps and tremors build a hidden layer of structure into the ecosystem's communication web. The tarantula's place in the food chain further emphasizes its ecological importance. As predators, they regulate populations of insects and small vertebrates, ensuring balance in a system where unchecked growth can destabilize entire niches. As prey, they support larger animals, from mammals to specialized wasps. Their seismic communication not only sustains their own survival, but indirectly influences the rhythm of predation and prey availability across the ecosystem. Each tap they make is thus part of a larger cascade, resonating through both biological and acoustic networks. Night deepens, and the tarantula retreats once more toward its burrow. Its body vanishes into the soil, but the earth continues to carry faint vibrations, messages left like echoes. The forest above hums with larger voices, but beneath it all, the spider's micro-signals persist, threading through roots and soil. To us, they are imperceptible. To the forest, they are vital punctuation marks in an unending story. And to the sound code, they are fine tuners, delicate beats that give clarity and precision to a hidden transmission spanning canopy, swamp, and river alike. The Amazon is never silent. Even in the depths of night, when the forest appears asleep, the air and water pulse with messages. A roar rolls across the canopy, shaking leaves with invisible force. Beneath the rivers, hidden sparks ripple through water like Morse code on a submerged wire. In the swamp, vibrations throb through mud and root, felt rather than heard. On the forest floor, millions of tiny clicks blend into a static hum, a rhythm carried by soil and tunnels. And in the leaf litter, a solitary spider taps and drums, adding fine punctuation to a conversation that spans miles. What emerges from this montage is not chaos, but a system, not a collection of isolated voices, but an orchestra of frequencies. Each creature, from the loudest to the faintest, has evolved its own way of overcoming the sensory challenges of the rainforest. The howler monkey rules the canopy with airborne sound, its roar carrying farther than sight could ever reach. The electric eel turns murky water into an electric medium, replacing light and vision with coded pulses. The caiman saturates swamp and soil with infrasound, signals too low for our hearing, but strong enough to travel across habitats. Leafcutter ants convert leaves and tunnels into drums, spreading vibration as traffic control and defense. Tarantulas, in their understated manner, add micro-signals that sharpen meaning at the smallest scales. None of them knows the other's messages, yet together they fill every medium the forest affords: air, water, earth, and the sub-base space beneath human perception. Science explains each of these adaptations as products of survival. The monkey roars to claim territory without fighting. The eel pulses to navigate and stun prey. The caiman growls to attract mates and intimidate rivals. The ant clicks to coordinate the impossible efficiency of its colony. The spider taps to woo a mate and guard its burrow. But place them side by side as we have, and another possibility emerges, that what seems to us like scattered strategies may be converging into a layered system, a broadcast built not by intent, but by evolution itself. Consider the principle of acoustic niche partitioning. In ecosystems where sound is crowded, from reefs to forests, species avoid overlapping frequencies by shifting their calls. Birds sing at higher pitches when insects dominate the lower ranges. Frogs call at night when diurnal choruses subside. The Amazon takes this principle to its extreme. The howler's roar occupies low-frequency airborne sound. Eels operate in electrical channels that bypass both air and light. Caimans drop below the threshold of hearing into infrasound. Ants and spiders shift into seismic cues carried by soil. The result is not interference, but complementarity, a spectrum divided into layers, each species transmitting on its own bandwidth. In this light, the Amazon resembles not just a habitat, but a communications grid, with animals as its transmitters. The idea seems speculative, yet the evidence lies in the forest's own responses. Birds time their songs to avoid the howler's morning calls. Fish alter their schooling patterns when electric pulses ripple through the river. Frogs adjust their rhythms when caimans rumble in the swamp. Even plants may respond. Recent studies suggest that root growth can be influenced by vibration, meaning the ant's drumming may indirectly shape vegetation itself. Every signal, whether intended for a mate, a rival, or a colony, spills outward into unintended receivers, shaping behavior across species. The broadcast is not a closed system. It is porous, shared, and constant. If we think in terms of engineering, each creature contributes like a component in a machine. The howler monkey provides the carrier signal, the loud bass line on which other transmissions can ride. The electric eel adds data in pulses, a kind of Morse code layered beneath the roar. The caiman anchors everything with infrasound, a bass line that extends the range into earth and water. Ants contribute rhythmic static, a steady percussion that stabilizes and reinforces. Tarantulas provide microtaps, fine tuners that give precision and punctuation. The combined effect is multi-channel, multi-medium, and continuous. Whether by design or coincidence, the rainforest is broadcasting on every available frequency. The question that follows is unavoidable. Is this system merely an accident of evolution, or does it serve a higher function? Biologists caution against over-interpretation. Evolution produces convergence without intent. Wings evolved in both birds and bats, not because they collaborated, but because physics rewarded flight. Likewise, multiple communication strategies can overlap without any hidden plan. Yet the scale of this layering is hard to ignore. Few ecosystems demonstrate such a perfect division of the acoustic spectrum, or such constant cross-species influence. If the sound code exists, it may not have been designed but emerged, an evolutionary broadcast network, accidental yet functional, like a symphony that writes itself without a composer. Still, the provocation lingers. If it is a code, who or what is meant to receive it? Other species clearly already respond. The jungle is full of unintended listeners, from insects adjusting their calls to predators exploiting hidden cues. The earth itself might be considered a receiver, as vibrations travel through soil and water, affecting growth, erosion, and nutrient cycles. Or perhaps, as some thinkers dare to imagine, the code extends beyond. Low-frequency signals like infrasound and certain electromagnetic pulses can travel extraordinary distances. Could the Amazon, through the combined voices of its creatures, be broadcasting not just within itself, but outward, into the atmosphere, the ionosphere, perhaps even into space? The thought may seem fantastical, but it carries a sobering undertone. Humanity has long considered itself the only species broadcasting into the unknown, sending radio signals skyward in search of contact. Yet here, in the oldest forest on Earth, other signals may already exist, encrypted in roars, rumbles, pulses, clicks and taps. They have been transmitting long before we learned to build antennas, long before we imagined satellites, and unlike us, they do not stop. The sound code, if real, is a broadcast millions of years in the making. There is irony, too, in our own role. As deforestation spreads, as rivers are dammed and swamps drained, the components of this code weaken. The roar of howlers vanishes when their territories are fragmented. Electric eels decline as water quality deteriorates. Caimans fall silent when wetlands are lost. Ant colonies collapse under agriculture, and tarantulas disappear with the leaf litter they depend upon. Piece by piece, the orchestra falls quiet. Whether or not the sound code carries a message for others, it is certainly vital to the forest itself. And if it fades, the Amazon may lose not only its voice, but its balance. The jungle at dawn illustrates both the resilience and fragility of this system. Mist rises over treetops as howlers begin their roar. Beneath them, electric eels pulse invisibly in the rivers, while caimans throb with infrasound from the swamps. Ants march endlessly across trails, clicking and drumming, while tarantulas tap faint rhythms into the soil. Each is only a fragment of survival strategy, yet together they weave an unbroken broadcast through air, water, ground, and silence. It is a chorus layered across frequencies, a living network that ties one of Earth's most complex ecosystems into something coherent. The final question is not whether the sound code exists, but how we choose to interpret it. Is it nothing more than overlapping survival strategies, or is it an emergent order, an encrypted message written by millions of years of life's persistence? Could it be the forest speaking to itself, calibrating its rhythms through countless voices? Or could it be something larger, a transmission waiting for recognition, meant not for us, but for whatever may be listening beyond? The Amazon leaves us with no answer, only echoes. The roars, the pulses, the rumbles, the clicks and the taps fade into the day, replaced by the ordinary clamor of birds and insects. Yet if one listens closely, beyond the limits of our hearing, beyond the biases of our perception, the broadcast continues. Always layered, always present, a hidden frequency network as old as the forest itself. And in that hidden signal lies a reminder. Life has always been speaking, in ways we are only beginning to understand.